Welcome to the first part of Statistics in Perspective. In this session, I'm going to be talking about summarizing your research data using descriptive statistics. This is simply organizing what you know about your sample and letting us know in a summary kind of a way. It is not testing any hypothesis about whether one treatment is better than the control or one treatment is better than another treatment. That's called inferential statistics, and we'll be doing that in part 2. So let's just talk about summarizing quantitative data about your sample. First of all, you want to describe your sample demographics. How many boys, how many girls, their performance on tests. You also want to take a look at what your data looks like. That's called a histogram. Does it look like it's rather normally distributed or not? And in this section is also correlations, which describe relationships among variables. So let's take a look at what kind of data you have. You will either have continuous data or categorical data. And continuous data are things like scores on a test or numbers on a scale that very often will start with 0 or 1 and go up by increments of 1. Examples are the MCA scores, the Ames Web scores, tests that you might develop on knowledge. Height is normally distributed. Age. If you have those kinds of scores, your descriptive statistics will be means or averages, the standard deviations, which means how far from the average they deviate, and the range from the lowest to the highest score. You probably also have scores that differ in the kind but not the amount. A rubric or a ranking is that kind of a score. So, for example, a 6 traits writing scale, even though it has numbers 1 through 6, they're not continuous, they're not equal intervals, so they're rankings. And interest inventory is the same thing. Pass-fail on a test, or the number of boys and girls, those are all categorical data. And the descriptive statistics you would use for that would be the percentages in each count or how many in each category. Here's an example of descriptive statistics on a continuous data for a study that I did on whether more boys than girls fail in reading. And at this point, I'm not testing the hypothesis yet. I'm just looking at how many boys I have versus how many girls. You can see that under N. I also looked at on nationally standardized tests, what's their average percentile? That's the mean. So you can see for boys, the average percentile is not the 50th percentile, but the 62nd percentile. For girls, their average score is the 64th percentile. So obviously, these children that I was looking at are from Lake Wobegon. They are from here in the Midwest. You also can see that the standard deviation, on average, 64% of all of them scored within 25 percentiles lower than 62 and 25 percentiles higher. So that's their average range. So right now, I'm just describing these boys and girls on their performance on a nationally standardized reading test. Now, here's my descriptives on the same kids using categorical data. So what are the demographics? My total N was 708. And again, you saw the numbers of boys and girls in the previous slide. I just transferred it to percentages now. So I had basically 54% boys and 46% girls. I also looked at the distribution of socioeconomic status among these kids. So free lunch, reduced lunch, pay, and full pay. You can see that free and reduced lunch are only about 20% of the total sample. So you could probably conclude from this demographics that my sample of children who were Midwestern children in the southeast Minnesota, Wisconsin area are probably not as diverse socioeconomically as you might have in a metro area. As far as what kind of district or residence that they lived in, I classified any town of 30,000 or higher as urban, and so 37% lived in not really urban areas as you would think of it, and those of you who live in the metro, but urban as opposed to rural school districts in Minnesota. You can also transform continuous variables to categorical variables in order to describe your sample. In this next slide, I'm going to show you how I took the screening for reading success overall score and transferred that to either a 0 at risk or 1 a pass. So any student who was at or below the 35th percentile on the achievement cluster or the language cluster was given a score of 0. Those who were at or above were given a score of 1, or above 35th percentile, I should say. I also did that on the dependent variable, the outcome variable. So I looked at their first grade and their third grade reading achievement scores, and if their total reading was at or below the 35th percentile on a standardized reading test, or they were identified for Title I or LD reading, they were given a score of 0. If they scored above the 35th percentile, their score was 1. By transforming those continuous variables to categorical variables, I'm now able to take a look at a contingency table or cross-breaks table. Again, this is just still descriptives. What it says is, of those who were predicted to fail by the SRS, how many actually failed by the reading failure criterion, and you can see that 80% did. And reading, pass, those that the SRS said would pass but did fail in reading, was 20%. So the SRS in kindergarten missed 20% of those students. Jean Chall has said that anything that identifies 75% of the kids who are going to fail later on is a good screening instrument. I wasn't real happy with having missed 20% of the students. However, the rest of the story is that by 5th grade, this test given in kindergarten had identified 89% of the students who failed, so only 11% had been missed. Now let's talk about describing relationships between variables with correlation. Correlation answers the questions, is there a relationship? How strong is it? And does the relationship suggest an hypothesis that could be studied or investigate the causation? So when you're looking at relationships between two variables, you could first of all use histograms to look at the distribution of each variable. You can use scatter plots to picture the relationships, and you can use correlational analysis for either continuous or categorical data. You can use scores on a test, that's continuous data, rankings or ratings, for example, stay-nines or high, medium, low, that's categorical data. Always remember, though, that correlation does not mean causation. The other thing to know about correlations, to be reminded of, because I know you know this, is that correlations can be positive, they can be negative, or they can be no correlation. There really is no relationship. So let's first start by looking at a histogram between the ACT composite and the high school GPA scores for students who are in our PASS program at St. Mary's, which is for students who ordinarily would not have been admitted because of either low ACT or low GPA. So you can see that both the GPA and the ACT are fairly normally distributed by the heights of the bars. You can also see the range of the GPA, and you can see the range of the ACT on this histogram. Now here's a scatter plot of the ACT and the GPA for the PASS students. And what I want to do here is to show you how you would draw a line through the middle, basically through the middle of the scores, to show the relationship. Now, when you draw that line, is the relationship negative, as one goes up, the other goes down, or positive, as one goes up, the other increases also? And actually, what you can see is the relationship is negative, which is very interesting, that actually as the ACT went up, the GPA went down. These are the histograms of the ACT and the GPA for our first-generation scholars. These are students of color who are on full scholarships. You can see that, first of all, their GPAs all cluster from 3.0 and up. In fact, there's one at 4.25 who took advanced AP courses, which counts for more than the 4.0. You can also see the composite ACT is a different, somewhat different shape. Now, when we look at a scatter plot of the ACT and the GPA for FGI scholars, my question is the relationship negative, positive, or unable to draw a line, therefore non-existent? And I would submit that this is non-existent. I don't see a logical place to draw a line, either ascending or descending, because the points are scattered all over the scatter plot. Now let's talk about judging the strength of the correlation. Anything below 0.40 is too small to have any significance educationally. Correlation of 0.41 to 6.0 is significant. It should have some theoretical value. It's a moderate relationship. Something that correlates 0.61 to 0.0 is very important. That's a very large relationship and should be paid attention to. If you get a correlation above 0.81, you probably have an error in calculation, or it's an extremely rare and strong relationship. So let's judge the importance of these correlations. The GPA and the ACT composite. For the past students, it's a minus 0.498, and for the FGI scholars, it's 0.029. So looking at these two correlations, would you say that it would be useful with either of these groups to use a combined GPA ACT cut score in order to accept them? Doesn't look like it to me. So the implications of these findings for criteria to use in selecting students for college admission is we should be looking at which one best predicts freshman grades, or is there something else that better predicts success in school? Now, what I'd like you to do at the end of this is to think about the descriptive statistics that you will use to describe your sample. So look at your demographic information that you have, such as sex, SES, reading scores, such as MCA, NWEA, or whatever, and list them under continuous if they're continuous, or categorical if they are not continuous variables. You don't need to have both, but I have space here for you to put up both of them. And what descriptors will you use based on that? Same thing if you have a pre-test. Is it continuous, variable, or categorical? And what descriptors will you use to describe and summarize that data for your sample? And then are you also going to do some correlations to take a look at that? So this ends part one of descriptive statistics. This should be the information that you need in order to give us a very full picture of the group or groups that you will be working with in your research.